Hi everyone, this is Professor M. Science, and today I want to talk about constants of motion in another one of our videos on rigorous quantum mechanics. As the name says, a constant of motion is a quantity that doesn't change as the system evolves in time. If you've studied classical mechanics, then most probably you'll have encountered constants of motion. For example, the angular momentum of a classical particle moving in a central potential is conserved. Central forces include gravity and electrostatic interaction, and one of the consequences of angular momentum conservation is that the trajectory of a particle stays in a plane. Today we'll explore what a constant of motion is in quantum mechanics. Let's go! You'll probably be familiar with constants of motion in classical mechanics. In the classical context, constants of motion are quantities that are conserved throughout the motion. In quantum mechanics, however, the definition is more subtle. We say that an observable A is a constant of motion if it obeys two conditions. The first is that it does not explicitly depend on time, so that its time derivative vanishes. And the second is that it commutes with the Hamiltonian. And this is it. Any observable A that obeys these two conditions is a constant of motion in quantum mechanics. The first condition makes perfect sense. The observable that we're considering should not explicitly depend on time if it is to be a constant of motion. The second condition may appear less obvious, but we should remember that in quantum mechanics, time evolution is given by the Schrödinger equation, which tells us that the rate of change of quantum states is governed by the Hamiltonian. From that point of view, it sort of makes sense that the Hamiltonian should feature somewhere in this definition, and in the rest of the video we'll see how this second condition leads to a series of properties that together mean that an observable can indeed be called a constant of motion. The first property of an observable that is a constant of motion is that its expectation value with respect to any state is time independent. To see this, we need to remember the expression for the time dependent of the expectation value of a general operator Q. It is given by two terms, one proportional to the expectation value of the commutator of Q with the Hamiltonian of the system, and the other the expectation value of the time derivative of Q. We derived this expression in the video on Ehrenfest's theorem, so check it out if you need a refresher. If we now use this expression for an observable A that is a constant of motion, we get that the time derivative of the expectation value of A is equal to a term proportional to the expectation value of the commutator of A with the Hamiltonian, plus the expectation value of the time derivative of the observable A. But, by definition of a constant of motion, A commutes with the Hamiltonian, so this term vanishes, and, also by definition of a constant of motion, A is time independent, so this derivative also vanishes. This means that the time derivative of the expectation value of a constant of motion is overall 0. The next important property of a constant of motion is that we can always find the common set of eigenstates with the Hamiltonian. This property arises directly from the fact that a constant of motion commutes with the Hamiltonian. We know from the video on compatible observables that we can always find the common set of eigenstates for two observables that commute. This means that we can write the eigenvalue equation for the Hamiltonian like this, and we can also write the eigenvalue equation for the observable A like this. In these equations, we label the energy eigenvalues of the Hamiltonian by En, and the eigenvalues associated with A by AP. The eigenstates here and here are the same for the Hamiltonian and for A because they commute. We label this common eigenstate with the quantum number N associated with the energy eigenvalue and the quantum number P associated with the A eigenvalue. From the video on the Schrödinger equation, we know that the eigenstates of the Hamiltonian are called stationary states. This is because if the state psi of our system at time t0 is equal to an eigenstate of the Hamiltonian, then the state of the system at a later time t is equal to this phase factor times the same eigenstate. As a global phase factor such as this one doesn't change the predictions of quantum mechanics, then the eigenstates of the Hamiltonian don't really change in time, and this is the reason why we call them stationary states. The extra feature we have now is that this initial state is also an eigenstate of the operator A with eigenvalue AP labeled by this P here. Looking at the state at a later time here, we see that it's still given by the same eigenstate of A, and the usual phase factor that doesn't change the physics. This means that if the system is in a stationary state, then the state of the system is also an eigenstate of A at all times. In turn, this means that if we were to measure A, we would always get the same eigenvalue AP. And for this reason, the eigenvalues of a constant of motion, the AP here, are called good quantum numbers. The final property associated with constants of motion is that the probability of measuring a particular outcome is time independent. Let's first write the eigenvalue equation for the Hamiltonian. We're going to assume we have a conservative system in which the Hamiltonian is time independent. We also consider again the eigenvalue equation for the constant of motion A. Let's now consider an arbitrary state psi at time t0. To study the time evolution of this state, we derived a recipe in the video on the Schrödinger equation for conservative systems. The first step of the recipe is to expand the initial state in the basis spanned by the eigenstates of the Hamiltonian. As usual, the expansion coefficients are given by this bracket. We can now immediately construct the state at a different time t, as given by this new expansion, where the expansion coefficients are related to the original ones by a simple phase factor. From these expressions, we can now calculate the probability of getting a particular outcome when we measure A at these different times. The probability of measuring AP at time t0 is equal to the absolute value squared of the corresponding expansion coefficient. I'm assuming that the eigenvalue is non-degenerate, but it would be trivial to extend this discussion to the degenerate case. The probability of measuring the same eigenvalue at later time t is now equal to this. Using this expression up here for C and P at time t, we can rewrite it like this. This phase factor has magnitude 1, so we end up with this. Comparing these two expressions, we see that the probability of getting AP for a measurement at t0 is the same as the probability of getting AP at a different time t. Overall, this means that when we measure a physical property that is a constant of motion, then the probability of getting a particular eigenvalue is the same at any time. And that's it. But let's recap before we finish. A constant of motion is a physical quantity whose associated observable obeys two conditions. The first is that it's time independent, and the second is that it commutes with the Hamiltonian. From this definition, we've then derived a number of properties associated with constants of motion. We found that their expectation value is time independent. We've also found that the eigenstates of a constant of motion are time independent. And we've also found that the probability of a measurement outcome of a physical property that is a constant of motion is time independent. With these properties, you can now understand why we call observables that obey these two relations constants of motion. Constants of motion in quantum mechanics are very useful because of the time independence of expectation values, of eigenstates, and of measurement probability outcomes. As a concrete example, angular momentum is a constant of motion in central potentials, which is really helpful when we try to then understand the behavior of systems like the hydrogen atom. I hope you liked the video, and please subscribe.